You may have seen land surveyors standing in the middle of the street with a bright orange vest, looking through something on a tripod at another person with a red and white rod. Civil engineers use tools like these for measuring angles and distances with great precision, so that buildings will be square, trains won't derail, and bridge builders will meet in the middle. Similarly, astronomers can use angles and distances for measuring distances to stars. As you may remember from geometry, triangles always have 180 degrees, divided between the three vertices. If you know two of the angles, you can subtract their sum from 180 to find the third angle. Likewise, if you know two of the angles and the distance between them, you can find the distance to the third, even if it's outside our solar system.
In our first example, let's imagine ourselves standing on the side of a river. Here is the river. It's a mighty rushing river that we cannot cross, but we want to measure from where we're standing over to that target over there. So we set up a scope with a protractor on it, and we sight the target down there. Then we turn 90 degrees to the right, and we sight down a line till we set up the scope a second time, precisely 80 feet from the first, precisely 90 degrees away from the first, and we set up the scope and we sight that target a second time. We find the degrees that time is 55 degrees. Now we have a triangle. We see 90 degrees and 55 degrees. We could do some subtraction knowing that triangles always have 180 degrees. That one over there must be 35 degrees, but we're not going to need that one if we're using the tangent ratio. So we take our two angles and our 80 feet and we go to the math. We know the tangent ratio gives you the opposite over the adjacent. When we plug in the values that we found, the tangent of 55 degrees is equal to the opposite over 80 feet. That's the adjacent. We've got our 55 degrees opposite the long one that we were trying to solve for. The adjacent leg is 80 feet. We're going to multiply both sides by the 80 so that the opposite side is isolated on one side of the equal sign. And when we do that math, we find 114 feet. 114 feet, I think that looks reasonable. Next, I'd like to discuss how parallax can be used to measure distances in the sky. Here I'm showing Earth and our distance from the Sun, which is 93 million miles, or 150 million kilometers. Those are pretty large numbers of a relatively small unit. Miles and kilometers work pretty well on Earth, but when we're talking about distance to the Sun or distance to other stars, you're going to want to have a much bigger unit of measurement so you can use fewer of them. 1 astronomical unit from Earth to the Sun. And 6 months later, we'll be 1 astronomical unit away on the other side. So between December and June, we are 2 astronomical units away from those two perspectives. In the last one we had a baseline 80 feet where we walked that distance. Here we just sit here for 6 months and we travel that distance of what? 300 million kilometers. That's a pretty good baseline. So if we measure the angle to a star and then 6 months later we measure that angle again, we've got a large baseline and 2 angles. We can do that geometry and estimate a distance to that far star. Also note its perspective to the other things behind it in the sky. Thank you to my lovely lab assistant with the pointer stick. Next, we are going to use parallax to measure a distance here in the lab, which I call a kitchen. I have taped paper to the chair so the paper doesn't move. I've measured the distance between these two crosshairs. They are precisely 5 feet. I know, I'm using feet, I should be using metric, but I don't have any metric measuring devices in my house. So the distance is precisely 5 feet, and using the tape and also a sight, show us the sighting thing, please. By sighting down the line this way, I was able to ensure that these lines do indeed point directly at each other. My daughter is over there holding a stick on the other crosshair.
Lab assistant.
We will line up the blue center line on the baseline, And now we will sight down this line until we're looking at the speck on the wall over there above the dog. Now that I have taped down my angle finder to the baseline, I can sight down the other one to my target on the wall and make them match. Then I'll be able to measure the angle between them. I have now measured and sighted the angles on both of them. You can see there I came up with 81.5 degrees, as well as my eyes could tell. On this side it was 83 degrees. My baseline between the two is 5 feet. I know this line does not project to this one, but it is parallel to the center line that did. I just couldn't draw through the middle of the angle finder. So here is my drawn model. I have my two angles, my 60-inch baseline and my mystery distance over here. How will we solve that distance?
And mystery drawing.